Well, hello everybody and welcome back. So here's the conundrum. I have this nice little set of headphones, and of course, you listen to them through your mobile phone or whatever, your mobile device. But it got me to thinking, I need to pick up a nice headphone amplifier so that I could, listen to these at home rather than just, something that'll really drive these high quality devices to their full potential. Because of course, I want to get the best sound quality when I'm listening to my headphones. So I thought maybe I'd invest in a nice headphone amplifier. So here's what I came up with. So here we go. We have a pair of, some of you may already recognize these, a pair of Carver Model Silver 9T magnetic field amplifiers. And you can tell from the little meter, they're rated at about 575 watts per channel. So those ought to really drive these headphones properly. All kidding aside, somebody sent these in, and they do have some issues with them, but physically they are in beautiful condition. And when we're done, we're going to go over these things all the way from the beginning to the end and restore them and make them work in their former glory. If that sounds like something you'd be interested in, or maybe if you're just interested in picking up a new headphone amplifier for yourself, stay tuned. I know this is going to be fun for me to make this video. I hope it's fun for you guys to watch it. So let's take a look and see what these things are all about. All right, so for those of you who are not real familiar with Carver equipment, the first thing we want to talk about is this model number can be a little bit confusing because this is the Model 9T, and there's also a Carver Silver 9 with no T. The Silver 9 actually is a huge vacuum tube amplifier, and pricing on those is extremely high. You can be up over $20,000 US for those. They're huge. They would hardly fit on this bench, and they were absolute masterpiece works of art. And this is called the Silver 9T. Now, I originally thought the reason they did that was because the 9T stands for transistorized. Makes sense. But really, what Bob Carver, or what I've read Bob Carver meant by that was 9T, meaning that it's tube technology. In other words, it doesn't use vacuum tubes, but he designed this solid state amplifier to have that warm, rich sound of a vacuum tube amplifier. So the T actually was tube sound, is what I heard. Nevertheless, this is a solid state amplifier, and it is a very high quality amplifier. But there's a few things we need that we can read about it here. So let's take a look at this spec sheet. So if you look, it's rated at 575 watts into 8 ohms from 20 to 20 kilohertz. And you can see into 8 ohms at 1 kilohertz, we're looking at 612 watts. Now, there's our first problem if we're going to work on this, because our little dummy load over there is only good for 300 watts per channel, and this thing will pretty much roast those. So bottom line is we're going to need to use something different. So I'll show you what I use for the big amplifiers, like if we're talking PA amplifiers that are big. I'll show you what I use. So big power requires a big dummy load, and what you see here is a 1000 watt 4 ohm non-inductive resistor, and you can see it has the the leads on it that are designed for, these are like the, the heat-proof wire. And these are 4 ohms, and I have 4 of them that I use, and I can just kind of attach them together and make whatever kind of load I need, anywhere from 4 ohms to 16 ohms, or I could do 8 ohms stereo at 2,000 watts or 1,000 watts. So lots and lots of power. And this is kind of the thing you need. Now these are, you can actually buy these online, and they're not really expensive for what they are. They're very accurate, and where you use these a lot is in like for magnetic braking. Like if you want to stop an electric motor like through the eddy currents, you can actually, like we use these in CT scanners, they have them to stop the gantry. The gantry weighs over a ton and it's rotating, and by shorting this resistor across the motor leads, it dynamically helps the thing to stop. It's like a brake, and that's why these are called shell braking resistors. And again, they come in different sizes. They have real small ones, and they go up to way bigger than this even. Some of them are huge. But this will take care of whatever this thing can throw at it. So that's what we're going to use. And conversely, the Silver 9 is just loaded with big KT88 vacuum tubes. It has about the same power output as these, but it has a separate tube chassis and power supply chassis, I believe. And you know, another benefit of it is while you're all sitting around the stereo at night listening to your favorite song, you can roast marshmallows off of the wonderful amount of heat that it puts off. So that's what you're looking at. Back to this spec sheet, a couple more interesting things. Obviously, when you look at the distortion, very good. Total harmonic is 0.5%, which is very respectable. And it's only from 20 hertz to 10 kilohertz, if you notice that. Your noise is negative 100 dB, A-weighted, referenced to the rated power, which is good. 2.3 volt RMS signal will give you your rated power. So it's, you know, you need a little bit of drive into it from your preamp, but that should be no problem. And look at the damping factor on the 9T. There's this is also, they have the specs for the 7T, which they're very similar. But the 9T, look, greater than 125 damping factor. So if you have a loose set of speakers that need a high damping factor amplifier, this will more than handle it. So bottom line, here's the really amazing thing. 1,400 watts of power it draws at full output. That equates to about 12 volts or 120 volts AC at just almost 12 amps. And so you could see two of these working together at full rated power is going to exceed your 15 or even your 20 amp American circuit. I mean, most American breakers circuits are, you know, lighting circuits are set at either 15 amp or 20 amp breakers. So you almost would have to have a split power rail, you know, one dedicated breaker to the right channel and one to the left to provide the current. And you can see accurate measurement depends on sufficiently stiff AC power supply. They really don't want your any kind of line drop. So if you have thin gauge wire in your house or a long run of wire from your main breaker to the outlet for this, it is going to adversely affect the performance of this amplifier. So you really need, if you're going to have something like this in your house, you really need the correct kind of power. So that's the kind of extremes you have to go to. This has a very unique power supply, and we're going to look into a little bit of detail in it when we get it apart and start working on it. Very interesting the way this is designed. It's really, really smart design of an amplifier. So let's check these out. I heard that they have some issues, so we're going to get them connected up and do some tests and see what it is they're talking about these are doing. Okay, we had a little slight delay because had to go out with my son to get a pizza because he was hungry, and made him drive because you know what they say. You give a boy a pizza and he'll eat for a day. Teach him how to drive to the pizza shop and he'll eat for the rest of his life. All right, seriously now. I have these set up in series, these two resistors, so we have 8 ohms, and they're connected to the speaker jacks. I have the signal generator set up for right now, but it's not turned on. And something kind of a little bit different that I've not shown any of you before, and that is I have my oscilloscope set up in a way that I've not shown you yet, and it is called differential mode. Now, this is a really important feature to learn how to use on an oscilloscope. And the reason for that is, and again, on this particular test we're going to do, it's not important. You don't need it. But there are some tests when we get into the alignment of this that this is going to be extremely important. And if you notice, the ground clips here on the oscilloscope are disconnected. We're not using them. And all we're using is the tips of the probes. And we have one end on our positive and one on our negative. And if you look at the oscilloscope, the thing that's a little bit different here is you look, I have channels 1 and 2 on add. And you can see the little arrows pointing to 1 and 2. And then I have channel 2 set to invert. And by doing that, what that's going to do is it is actually, this trace is now, the vertical deflection of this trace is going to be controlled by the difference between the center posts of these two connectors. So this is called differential mode because it's looking at the differential voltage between these two tips of these two probes. The reason this is important is we are not connecting anything electrically to the outside, right here, the outside part or the grounded part of the probe. And why that's important is, as we talked about in our little oscilloscope tutorial, losing my voice here, the outer ring of your BNC connector for your probe port is actually physically connected to the ground prong of your cord. So if you look at the power cord here, this ground prong is actually connected to those jacks on the outer ring. What that also means is anything that's connected to, this ground probe, when it's connected on there, is also going to be connected to ground. So anything that is connected to your AC outlet and is unisolated, you pose a risk of a severe short. At the very least, you will blow this wire apart. At the very most, you could cause a fire, you could damage the equipment, you could get shocked or electrocuted. Very dangerous. This isolates that. Now, I still would put the scope on an isolation transformer if we were going to do that. But there are some tests that that we will use the oscilloscope in here, and you will actually be putting your scope at mains voltage potential on the mains. The instructions tell you to use an isolation transformer of the scope. It's still not my favorite way of doing things because even though it's isolated electrically on that transformer, you're still putting one leg of your AC on that outside ground terminal, which I still don't like it. So even in addition to the isolation transformer, your best bet is to use this differential mode. So I thought I'd show that to you. If you notice, there is only one trace. It's not dual trace. Even though we're using 2 channels of the scope, there's only one trace. And that's because we're only showing the differential signal between these 2 probes. So technically one could be acting like the ground and one is acting like the center, but it's really different. It's isolated. They also make a special probe called a differential probe, which actually has a big box that plugs onto the end of your connector, and then there's a probe tip on it, and it basically does the same thing. It gives you an isolated signal that you can measure, and you can also measure very high voltages with some of those. So just a couple things that you can use. But this is a technique that you might want to use, again, whenever you want to isolate your scope from any kind of voltage. So there you go. So we're connected up, and we're just looking right across our dummy load here. And the first thing we're going to look at is, I'm going to turn the voltage down on the scope a little bit, and we're just going to look if there's any kind of noise at the speaker terminals when we power up. So we're sitting at about, let's see here, we're looking at 1 volt per division right here. And I'm going to plug this thing in, and I'm going to turn the amplifier on, and we're going to check and see what happens. You hear that little bit of buzz, and everything looks good so far. And again, my trigger's a little bit off here. And take a look what's happening here. And you can see there's a little bit of a pulse, and you can see it now. It just goes right off, and now we got a big noise spike. And remember, we're at about 1 volt per division. So I think this is the hum that the owner was talking about, and that part, it really shouldn't be getting out to the speaker terminals. I believe what that is the triac of the soft start circuit doing its job. But until it comes up to full voltage, it's supposed to, the speakers are supposed to be snubbed out, I think. I don't know. So now, if I take this up to a higher voltage, and I'm going to put 100 millivolt RMS into the input, and we're just going to see if we get any output. And there you go. And if we just kind of increase this a little bit. Now, the first thing I notice is I have a, okay, it's a high frequency right now, so let's turn our frequency way down. Okay. And you can see, I don't know if you can see, I can see it really clear, but if you look right here, and you look right here, you actually are seeing crossover distortion, even at low power. So we don't have a whole lot of power right now, and I can increase the output a little bit, and you still see that crossover distortion. You can see it very clearly right here now. I'll move it into a center of a graticule where you can actually see it. So there it is, and there it is over there. And right now, we're not putting out very much power. You know, we're only a few watts, but still, it's already starting to. You have that crossover distortion, and I think if we increase our power even more, that crossover distortion really never goes away. And we're putting some serious power out now, believe it or not. Our little resistors are singing a little bit. But we still have that little crossover distortion. So I'm thinking we're probably going to need to look at this inside a little bit. At the very least, it's going to need some alignment work done to it. Let me turn that back down because we really don't want to run this too hard while we're talking. And so there you go. But it is working, and at least we know before we even take a cover off or try anything at all that we are getting some action out of this thing. It is functioning. So there you go. Let's get some covers off and see what's going on inside. Okay, we have it all apart here, and as you're going to find out, this is not going to be your average amplifier, and this is definitely not something that somebody who's just getting into this type of thing is going to want to tackle for repairing or recapping or anything. This is a very unique design, and it's not like anything I've ever worked on before, and probably not like much of anything else that's out there. So the top comes off like this, and then there's those two top covers that come off. Then you remove the wires from the back of the meter, and pretty much everything else is long enough, the wires are long enough that you can kind of slide this out of the way. Now, like I said before, this is very unique. First of all, this thing puts out almost 600 watts, and that's into 8 ohms, and I believe it can do up to 1,000 watts into 2 ohms. So this is a very powerful amplifier. But if you look at the transformer here, it's quite small for what it is. And if you all recall some of the videos we did on some of the other equipment, like the SX1250 had that great big toroid transformer, and it was only running 2 160 watt channels, so that would be 320 watts, which is still far less than this one. The Sansui 9090 is only 110 watts per channel, so that if you added those two channels together, that's 220 watts. I know I'm simplifying my description here, but if you recall, it had an enormous, almost double the size of this transformer. So how does Carver get away with this? Your first reaction will probably be what mine was, and I look and little 9,000 microfarad capacitors, and I say to myself, well, how can this thing work? Well, first you have to understand the topology of this, of how it's built. It is nothing like anything that we've worked on this channel so far. So I'll try to, and again, I'm not an expert on anything Carver. This is something that I don't deal with very often, and so it's a learning experience for me along with you. But I'll share with you what little I do know, and kind of let you see how I'm kind of amazed by this. And honestly, it'll be pretty cool to see how it works once it's all set up and running properly. So let's get into this, and I'll show you a few things. Okay, so the first place I think we should start on this thing, in its uniqueness, is going to be the power supply. Now, when we first look at a standard power supply in a lot of these amps, they're pretty basic how they're designed. Let me see if I can dig up a schematic real quick and kind of give you an example. So here's a little schematic of the block diagram of the SX1050 or 1250 that we just did a video on not too long ago. You can see that it's a pretty standard design. So you have your main big power transformer, and you have your primary winding. And the primary winding, as you notice, has the little soft start circuit, and we talked about how that works. And then you have 3 secondary windings. The first 2 here, these great big ones, are going to be your power for your right channel and left channel power amplifier. So there's a bridge rectifier, and you have your ground, and you have your positive power supply and negative power. And then these are those great big 22,000 microfarad capacitors. And this over here is just a linear regulated power supply, and it produces all the voltages for all the lower voltage, lower powered parts, like the tuner, the preamp, the phono stage. All that comes from this power supply. And it's very traditional. This is what you're going to see in just about every amplifier you see out there. And really the name of the game is, to have a very good sounding amplifier, you need a really solid power supply. So typically this is going to be a big, huge transformer. It's going to have a very high current secondary, very big diodes, and then massive storage capacitors. And these capacitors do more than just filter the AC hum. They actually act as kind of like a storage buffer for high current. So whenever you have a very high, like a high transient, like for a large base node or something, where it's only a short-term high current draw in the power supply, these filters actually do more than filter. They actually provide high current for that short time. And by having large capacitors, this is how you increase and improve the dynamic power of the amplifier, as opposed to the standard continuous power. So you have your continuous power, which is the way you test it typically, is you put an AC sine wave, continuous sine wave into the amplifier, and then you get the AC sine wave out of the amplifier into a resistive dummy load, and you just measure how big of an amplitude you can get in there before it starts, the sine wave starts to clip and distort, and then you use Ohm's law to calculate, based on the RMS value of the voltage you measure, how many watts are being dissipated into the resistor before distortion. And then to measure dynamic power, though, you would just put a burst of a signal in there, and you would kind of look at the maximum peak you would get there without clipping for a very short-term period of time. And these are going to be a direct influence on that. So that's why you normally see in high-quality amplifiers anyways, these great big capacitors like this. And as you can see, there's only a couple of components here. You have a bridge rectifier, which is just 4 diodes, and 2 capacitors. It couldn't be simpler. It's been like that forever. Of course, we go to this, and it is nothing like that. So let's talk about this for a minute. Okay, so here's a little diagram of the power supply that's in this Silver 9T, this Carver. And the first thing you'll notice is you still have a transformer, and if you recall, it was physically smaller than we're used to seeing in other amps. Uh-oh, took off my microphone. Huh? Did you hear that? So, again, if you didn't pick that up, this is physically a smaller transformer than we're used to seeing. And here's the primary side of the transformer, and you can see how much is going on this side. Now the first thing, these 2 coils, or these 2 primary windings, you find these in a lot of amplifiers, and all these are both 120 or 110 volt windings, and you can connect them in series or in parallel, so that this will run in the United States, for instance, where we have 120 volts, or over in Europe where there's 240 volts. So that's all this little switch is doing, is letting you select the incoming voltage. But if you notice, there's some other components here, and they're wired right in line with your AC power cord. Now this first thing here is just a noise filter. This is like a, for filtering out EMI, things, any kind of RF noise or anything to clean the lineup. Number one, to keep things from getting in, and also to keep noises from here getting out. That's another thing. Now the other thing is, you have this little circuit board here. See this dashed line? And there's an opto-isolator. There's a little bridge rectifier, and these are little small diodes. There's a network of transistors and some resistors. And down here is the most interesting thing, and what it is a triac. Now a triac works a little bit like an SCR, except it will conduct in both directions, okay? Whereas an SCR works just like a diode when it's gated. This one also has a gate, but it also, if you look, the symbol is almost like 2 SCRs wired back to back in reverse polarity. And really what this is an AC switch. Now you see these very often in light dimmers, like the little dimmer switches you get in your light socket in the wall, to be able to, with the little knob to turn it up and down. all those have in there is a simple little circuit with one of these triacs, and the triacs can turn on and off to chop up that AC waveform to allow less or more of it out, which essentially reduces the voltage and current out to your light bulb to make it dimmer or brighter. They're doing a similar thing here. Think of this as a light dimmer. And this circuit in here is responsible for turning it on and off. And what this circuit is doing is it's monitoring the line current, and it's regulating whether it needs to turn it up or down based on this little monitoring circuit. Now, this is your power switch. This is the first thing I'm a little bit concerned about on these. The power switch, all it really does is it shorts out a capacitor here, and this capacitor is actually here for sensing is for phase sensing, for when your phase is going positive or negative. By shorting this out, it prevents these transistors from ever turning on, and it prevents the triac from ever firing. So really turning the switch off turns the amplifier on. There is no place in here where you're actually breaking the circuit. The triac is actually the only thing that breaks the circuit. So, in a traditional piece of electrical equipment, you would have a power switch right here, and the switch would physically interrupt the AC going into the rest of the circuit. This does not have that. So as long as this is plugged into the wall, this is all energized here. And the only thing that will block the voltage from getting into the primary of the transformer is the fact that this capacitor is shorted out, and it's not biasing these transistors, and it's not firing this triac. That's a little iffy to me. I've seen these fail way too often. We use them a lot in X-ray to control different things, and I've just seen them short way too much. And if this shorts out, there's really no other way to shut this thing down. Anyhow, beyond that, what they're really doing with this is they're actually monitoring the voltage, and that monitoring goes into this little opto-isolator. So it's an isolated circuit. So your AC line is physically isolated by this opto-isolator IC from the rest of the power supplies. And it's changing the duty cycle of this triac firing on and off. So if the voltage starts to drop, this fires harder, allows more current to flow through the primary, which allows more to come out of the secondary. So really what this is a regulated power supply. It's just not regulated like most of us are used to seeing. So what's the advantage of this? Well, think of it. Anytime we regulate a power supply in a linear power supply, we typically start out with a voltage that's higher than what we need. And then we take that voltage and we absorb some of it into either a semiconductor like a transistor or into a resistor or something. And that excess energy is bled off and converted into heat. You can see how this would be a very inefficient thing. Number one, it produces a lot of heat. So if you remember in our Pioneer stereo, those transistors would get very warm in the power supply section, the regulator transistors, because all that excess voltage above and beyond what you want the power to be has to be converted into heat and dissipated into the heat sink of the transistors. The way this works is it only provides as much energy as this needs to be at the proper voltage. So you're not really bleeding anything off into heat, or at least a minimal amount. That makes this power supply very efficient, and it doesn't have to provide as much energy because you're not wasting a lot of energy on heat. So that's a good thing. Now, we get on the other side here, and this is where things start to get kind of strange. We have one bridge, two bridges, three bridges. Now, these ones are individual discrete diodes. This one isn't actually a bridge rectifier module, a big 25 amp heatsink mounted. So let's take a look at some of this. Here's your incoming line filter that we were looking at. You can see they even have a little diagram of it on it. And your AC power cord just comes straight into here. Other than having a fuse in line, there's no switch here. Notice there's no power switch. It comes out of here and it feeds into this board, which is this circuit right here. And you have this little triac here. There's your triac, and it's a power triac, so it can handle quite a bit of current, and it's on this heatsink plate. By the way, this whole bottom of this chassis is a heatsink. It's just a giant heatsink. The triac is then controlled by this voltage regulator board, and you can see here's your network of transistors. There's your little opto isolator for your power detection, and you have your capacitor for phase detection, or your phase detect capacitor, and your little diodes, that little diode bridge. And these purple wires right here, hold that thought. Okay, so you see this little purple, these two purple wires here, they go right over to the power switch. So you see my power switch right here, and they essentially just short out this capacitor right here, and that's what keeps the triac from firing and keeps the machine from turning on. And again, I like to physically interrupt the electricity going into a device. I don't ever like anything where there's active voltage somewhere like that. But that's the way they did it on this. They have a lot of faith in this triac, I think, and but that's how it works. So this is your regulation board and your phase detection board, I guess, whatever you want to call it, your triac. That then comes out and goes into all of those taps of your power transformer right here. So you can see all those going in. Comes out of there and it goes back here. You see these two big capacitors. You have your large 25 amp bridge rectifier, full wave bridge rectifier right here. And then if we turn this around, you can just kind of see in this big mess of wires these large diodes, and there's 8 of them here. So this is the remainder of the power supply. So you have your power supply board back here. Now, if we go back to our schematic, why are there 3 different bridge rectifiers? Well, we have 3 main power supplies. We have a 31 volt plus and minus, positive and negative 31 volts. We have a positive and negative 67 volts. And we have a positive and negative 118. And the 118 volts is where you have these two 9,000 microfarad capacitors rated at 125 volts. So these things are running pretty much at their maximum capacity, just about. Now, you might ask yourself, why are we having all this? What do we need all these crazy voltages for? Because we also have an 11.4 volt supply. So we have that runs, takes care of some of this stuff up here and the drivers and all that. But why do we have these 3? Then they're all 3 high current power supplies. They're all pretty big. If you notice, there were some pretty big capacitors back here too. These 2 big blue ones and those 2 big black ones in behind there. Those are not little either. They're pretty good sized. So what is all this stuff? Well, let's take a look. Okay, the next part we're going to talk about is the actual amplifier section itself. And it's really hard to get all this in shot here on the camera. This is the amplifier board, and it's a big long board. You can see it goes all the way, from here all the way down to here. This is all the amplifier board. And mounted to the bottom of the chassis is a whole bunch of transistors. So you can see there's an entire row of them starting clear back here, and going all the way up to, clear up to here. Try to get it all in camera. And then on this side, same thing. And the unique thing about how this thing's built is the transistors actually pass right through the circuit board, come out on the other end of the circuit board. These are the leads from this transistor. Then they literally loop around, hook and pinch a wire onto the end of the lead of this transistor and then move it over to here. So essentially these transistors are tied in parallel, and these are in parallel, and it's like that. These are paralleled sets all the way down. Kind of a strange design how they did that. There's a lot of things in this amplifier that is kind of strange. Like when you look at things like this on the board, kind of a little bit of a bodge job, but you can see components kind of sticking off the board and tacked on. You can see on this side where there's a transistor on this end, and then it comes through the same way, and it's kind of connected to this transistor, and then this transistor has a little resistor tied on this leg and then goes into here. Those all kind of look like afterthoughts that they put on this, but I assure you this is an all original amplifier. It has not been serviced. So pretty unique. Now you would think that in a traditional amplifier these ganged transistors would all be ganged together for your push-pull section of your output. In this instance, though, that is not correct. Believe it or not, there are only, well, let's look at the schematic to make a little more sense of it. Every time I look at this schematic, I laugh because it's just not something you're used to seeing. Very, very unique. And again, I don't know whether to like it or not. I respect it though. So these 4 transistors here, 1, 2, 3, and 4, right here, those are your actual outputs. All your 600 watts or whatever, 4 transistors. Now, you also have these big ganged sets of transistors. So here's 1, 2, 3, 4 ganged up here, 2 more ganged up here, 2 ganged down here, and 4 more ganged down here, plus all these drivers or voltage amplifiers, whatever you want to call them. So I'll try to explain this as best as I understand it. And again, I'm not an expert on this, so don't take everything I say as gospel, because, you know, I know this enough about this to be dangerous. But essentially what's going on, Carver refers to this row of transistors and this down here, and this row of transistors and this right here. They refer to them as commutator sections. Now, why do you need a commutator section? What's that? Well, I'll try to explain it. If you notice on the top and on the bottom, you have 3 separate power supplies. Okay? You have a positive 118 volt, a positive 67 volt, and a positive 31. Then you have the same thing down here, negative 31, negative 67, and negative 118. And essentially, at low volumes or no volume, if I understand everything correctly, what's happening is these commutators here and these commutators here are pretty much sitting idle. They're turned off. So you have these steering diodes here, and what you're going to see is this 31 volt supply going down into this set of outputs, and the negative 31 volt supply going through this diode into this set of outputs. And so essentially this amplifier runs at low power with a plus and minus 31 volt supply, which is a typical supply you would see on a low wattage amplifier. As the amplitude of your drive signal over here at your input section increases, all this control circuitry will begin to bring in these commutators, and these commutators, once we exceed the swing up and down of that plus and minus 31 volts, it will begin to bring in the second power supply by turning on these sets of transistors. And it will commutate the 67 volt supply into here and increase the voltage and give you more voltage to swing up and down to make more output amplification. As we start to grow beyond that, then these 118 volts, and these are the big guys, they'll kick in, and this set of commutators comes in, and these steering diodes actually prevent this power supply from interfering, backfeeding into these ones. So you could see they're isolated by diodes. So essentially, why is this important? Why would you do something goofy like this? Okay, well, there's a good reason, and that is, in a traditional amplifier, you would take all these transistors and you'd gang them all up in a big gang. So the more power that you want, the more transistors you'd put together in, in parallel, the more parallel sets. So if you look at some of the, like the PV amplifiers and the crowns and the big ones that you see used in commercial audio and so forth, they just have tons and tons of transistors stacked in parallel to be able to handle the higher current and voltage. And then they have two great big massive power rails, and the amplifier will be sitting at an idle current, and that current can get very high on those. So once again, we're converting a lot of energy into heat that's being burned off just to have the amplifier sitting at class A or wherever it needs to be, depending on the design of the amp. And then the amplifier will turn on those transistors only partially, unless you get to high volume levels and you turn them on the whole way to allow the full swing of the voltage, up and down for maximum amplitude. What this does is it ensures that these things are always working in a wider range, and then it just provides different, it's like having 3 different power amplifiers built into one, so you can kind of run this at low, medium, and high. It's almost like a transmission in your car with 3 gears. But they're automatic gears, and they are brought in not rigidly. They kind of turn on as they need to, but they're controlled by this whole circuit back here. And again, the electrical engineering behind this is beyond my ability to completely explain it properly. But that gives you just a synopsis of how this works. So when you look at these big transistors all here that are stacked up, you're really not looking at a whole two paralleled sets of PNP and NPNs, but rather you're looking at 2 sets of commutator transistors and then 4 main outputs. And they only call these 4 transistors here 1, 2, 3, 4. They just call these are actually called your outputs. The rest of them are called commutators. So it's very interesting. Although the commutators don't come in hard, in other words, they don't just switch totally on and totally off, they actually come in as needed. Now, as these supplies begin to sag down, that voltage monitoring circuit that we saw on our power supply will cause the this triac to fire harder and boost this up. This is why you don't need great big capacitors. These 9,000 microfarad capacitors for the big outputs, and these smaller ones are all you need. Same thing with this smaller transformer. Everything's done is like pulsed energy. The thing that amazes me about this amp is the fact that it can react to the sound quickly enough to turn all this stuff on without causing any appreciable distortion in the output. That's the thing that impresses me about it. So if you remember earlier when we tested this, there is a crossover distortion component, and it does it at all volume levels. So obviously one of these adjustments is out. The other thing is, if you read the theory of operation on this amplifier, they talk a whole lot about the importance of some of these capacitors in here for monitoring phase change and things like that, and timing of charging. And they talk about, for instance, where was that capacitor? This network up here, this 47 at 16, and this Zener diode. There's a couple other caps here, this one. Several of the capacitors in here are extremely critical to these commutators working properly. So if ever there was an amplifier that it would be very advantageous to do a recap on it and make sure that the capacitors that are in there are exact replacements. You do not want to mess around at all with the values of those capacitors. Whatever is in here, you want to replace with the same exact values, because you do not want to affect that timing that's going on. So you can kind of see how complex this circuit is. It doesn't look like much to look at it here. It looks like a very simple circuit, but it's actually very complicated. And it's not something you want to service unless you really have the equipment to do it and you understand how to do it. Now, I'm going to just kind of, this first video clip is just going to be an overview of how this all works, which is what I just did. The next video, I'll go ahead and do the recap on this, which is simple. There's not a whole lot of components like that that need, most of these things are permanent. They don't fail. You don't have to replace them or mess with them. But after I get that done, we'll do a second video, and we'll actually go through the tedious process of doing the alignment on this, and you'll see what I'm talking about. The alignment on this is unlike anything you're ever going to see. When I talked earlier on my video about using an oscilloscope in differential mode, making sure that you have an isolation, this is why. One of the things we're going to look at is we're going to look at the phasing and the firing of this triac. And you're going to be putting that oscilloscope directly on this. This is directly connected to your incoming mains. There's no transformer isolation at this point. It comes right out of this filter, which comes right out of the AC power cord. And therefore, anything that's on here is going to be live at mains potential. You never ever want to put a ground pin from your oscilloscope probe. Never want to put the ground here. You do not want that to come in contact with this, because essentially what you're doing is you're taking that ground pin, which is connected to the center ground prong of your power cord, and you're just shorting your mains straight to earth ground. So you either have to use an isolation transformer, which I'm against that, because even with an isolation transformer, that ground terminal on your oscilloscope will be sitting at mains potential. If you touch the chassis of your oscilloscope to anything else, you could essentially, even with an isolation transformer, you could come in contact with high voltage. So we absolutely, as soon as we connect this here, so we certainly do not want to do that, and therefore I recommend using that differential mode. If you don't know what you're doing, this is not the amp you want to start working on. Take it to a professional, take it to somebody who knows this product, or send it back to Carver. To my understanding, they do work on even out of production equipment they will service. So there you have it. So let's get this done. I'm going to post this video, and main reason I'm doing this one on video is it's so interesting how it's designed. It's not like much of anything that we've ever seen on this video or on this channel. So, all right, very good. I appreciate you all coming along. I appreciate all of you that watch these videos. I wish you all the best. Peace, joy, happiness, and good health in your lives. And until next time, be well, and we'll see you soon.